Hello guys, and welcome to today's video. Again, we are learning about phase margin, gain margin, phase crossover frequency, and gain crossover frequency. Now we are going to be building on the knowledge we learned from the last video about Nyquist criteria to understand what phase margin, phase crossover frequency, and gain crossover frequency is. I might not really define this terminologies in the standard way. I'd advise you to read your textbooks or read your lecture notebooks to know how the lecturers define it. But the purpose of today's video is so that at the end of the video you will understand these terminologies and you might be able to put them in your own words. Is that okay? So let's dive into phase margin, phase crossover frequency, and gain crossover frequency. We'll do that by analyzing the Nyquist plot for this particular transfer function g of s equal to k divided by s into 1 plus t1s and 1 plus t2s. Okay, besides, this is called a type 1 transfer function. Okay, type 1 transfer function because the power of s, okay, the power of this term s is 1. If the power of s here is 2, it will be type 2. If the power of s is 0, it will be type 0. Type 0 looks like this: k divided by 1 plus t1s and 1 plus t2s. Okay, there could be only one factor or there could be as many factors as possible, but the most important thing is you use this s, okay, as the yardstick to define the type. You'd use the power of s to define the type of the system. So for this type 1 system, the Nyquist plot is given as this purple diagram here, this purple diagram that you see here. Now the yellow circle is called a unit circle. Okay, so this is a unit circle. Then the Nyquist plot is this plot. Remember that we got the Nyquist plot by plotting what we call a polar plot. A polar plot, okay? Polar plot is magnitude versus phase. Magnitude versus phase. So magnitude versus phase is what gives rise to these polar plots. And magnitude versus phase is usually in form of radial lines. The radial lines are the magnitude, then the phase will tell me the direction that the radial line is pointing to. So when you vary your angular frequency from 0 to infinity, you take note of the infinite radial lines that occurs, and that's what gives rise to this plot that you're seeing over here. So this is the Nyquist plot for the function g of s is equal to k divided by s into 1 plus t1s and 1 plus t2s. Now it's important you memorize the Nyquist plots for some standard g of s. I defined in the last class on Nyquist criteria different Nyquist plots for different types of transfer functions or different types. Okay, you should check that video out to see the different types of Nyquist plots for different types of transfer functions. So now that we've established all of this, since we are talking about magnitude versus phase, it's also important we label our axis. So this is 0 degrees, this is minus 90 degrees. When you're going in the clockwise direction, you label with negative angles, minus 180 degrees, and this is minus 270 degrees, and so on and so forth. So if you're going in the counterclockwise direction, you label with positive angles. Now when we are talking about phase margin and gain margin, okay, we are interested in how our Nyquist plot behaves around one important point called the critical point. Since this is a unit circle, then this should be minus 1. Okay, or this point is minus 1, 0. So minus 1, 0 is the most important point in control system. It's the point that demarcates a system from stability and instability or marginal stability. Now, we want to make sure that our Nyquist plot always remains within the boundaries of the unit circle. We don't want Nyquist plot to pass the unit circle or to pass through this particular minus 1 point, or we don't want it to be above the point. We don't want it to spiral like this, or we don't want it to spiral through the point. At all times, we want to keep the Nyquist plot within the unit circle. So we are interested in 2 points. I can call this point B and I can call this point A. So for A, there is an angular sweep that point needs to sweep in order to get to this point, while for point B, there's a horizontal dash that the point B needs to trace to get to this point -1. So these points A and B will help us to understand the phase margin and the gain margin respectively. Now, the angular sweep can be gotten when you join this line to the center. Remember, this is a unit magnitude. From here to here is 1. So the angular sweep is what we call our phase margin, phi of m. So that angular sweep that is necessary to take the system to instability. Okay, remember, when the system is on this point, or when it encircles that point, the system is now unstable. When the Nyquist plot passes through the point -1, or when the Nyquist plot encircles that point, the system will be unstable. So the phase margin tells us the extra lag, the additional lag is required to drive our system into stability. Okay, that's the phase margin. Okay, so the phase margin is actually gotten when the magnitude of our G of S is unity. Now, we need to take note of the frequency, okay, that gives birth to this particular phase margin. The frequency that gives birth to this particular phase margin is a frequency that will cause the magnitude of this particular Nyquist plot to be unity. We call it the gain crossover frequency. Simply put, WCG. So the frequency of the system at this point is the gain crossover frequency. The gain crossover frequency is the frequency where the magnitude of our G of S is 1. Okay, the magnitude of this transfer function is 1. So when the magnitude is 1, we can be able to determine the phase. Okay, so there is a particular magnitude and there is a particular phase theta. Okay, and that theta is going to be obtained at this frequency WCG. So that's how you find this particular phase margin. So to get phase margin, you find this frequency. Then after getting this frequency, you compute this theta. Then if you now want to get your phase margin is now going to be 180 minus theta. But since theta is already a negative angle, we can say 180 plus theta. A more standard way of representing the phase margin is going to be 180 then plus theta is regarded as the phase of our G of S, okay, when the frequency is equal to WCG. Okay, phase of our G of S when the frequency is WCG. So that's the phase margin. Now, there's another thing we need to consider, which is the gain margin. Remember, this point B is very close, or sometimes maybe far away from the point -1. But at all points, we don't want this point B to get to this point -1, or we don't want it to be at the back of this point -1. We always want to keep it behind or within the confines of the unit circle. That is why we have to consider the distance from B to the origin here. So we can label that distance as, let me call it alpha. Okay, so if from here to here is 1, then definitely from here to here, which is alpha, is going to be less than -1. So with that, we define our gain margin as the ratio 1 divided by alpha, 1 over alpha. Sometimes the gain margin is expressed in decibels, so you have 20 log 1 divided by what? Alpha. So 20 log 1 divided by alpha is taken as what? The gain margin, where alpha is the distance from here to here, and alpha should be less than 1. Alpha should be less than 1. So if our system must be stable, alpha should always be less than 1. Now, alpha is actually the magnitude of the system. Alpha is the magnitude of this system when the frequency is a particular value here. So when the frequency is at this particular value, we can measure alpha. So the frequency that gives rise to this function having a magnitude of alpha is what we call the phase crossover frequency. The phase crossover frequency, we write it as WCP. So simply put, the phase crossover frequency is the frequency, okay, when the magnitude of this function lies on the minus 180 degree line. So the frequency, okay, where the magnitude of this function lies on the minus 180 degree line, or you can simply say that the phase crossover frequency is the frequency when the phase of this system is minus 180 degrees. The phase crossover frequency, the frequency when the phase of g of s is minus 180 degrees. So the phase crossover frequency, WCP, is the frequency at which the phase of g of j omega or g of s is equal to minus 180 degrees. Okay, that's the phase crossover frequency. So there's another one that I defined for us. I defined the gain crossover frequency, WCG, as the frequency when where the magnitude of g of j omega, since s is equal to j omega, is unity. Okay, so important point to note: if we want to calculate the gain margin, first of all we need to calculate the phase crossover frequency, because the phase crossover frequency is not just the frequency at which this particular phase is minus 180 degrees. It's the frequency where the magnitude of this particular polar plot is going to measure at alpha. So another way of writing this alpha is, you can write your gain margin as 20 log, okay, 1 all over the magnitude of g of j omega. Okay, you're calculating this magnitude when omega is equal to WCP. Okay, so that is how we write our gain margin. Gain margin is 20 log 1 all over the gain at the crossover frequency. Okay, that's gain margin. So the you can as well write this, because of the property of logarithms, this becomes minus 20 log, okay, the gain, the magnitude of g of j omega when omega is equal to WCP. Okay, so 20 minus 20 log the magnitude of our transfer function at the phase crossover frequency. Okay, so while we calculate our phase margin by finding the phase when the frequency is at the gain crossover frequency, so in the following calculations, or in the following examples after this particular video, we are going to try to use our knowledge of phase and gain margin to test the stability of systems: phase margin, gain margin, phase crossover frequency, and gain crossover frequency, to test the stability of systems. Now let me just say something about phase margin and gain margin. For our system to be stable, I've already established that alpha should be less than 1. So alpha has to be less than 1, because if alpha is more than 1, that means this point B would have crossed over this minus 1 point, which I don't want. We don't want in control system. So alpha must always be less than 1. So if alpha is less than 1, that means this particular value, this ratio will always be greater than 1, and the log of any ratio greater than 1 will be positive. So for stability, the gain margin should always be positive. So how about the phase margin? So remember that we said phase margin is 180 degrees plus theta. But remember, theta is a negative value, and theta is simply the phase of our transfer function when W is at the gain crossover frequency. That's the frequency that causes the magnitude to be 1. So this is going to be a negative angle. So if that angle is negative to a very good extent, okay, then 180 minus a negative angle, okay, should give me something positive. But if that angle is bigger than 180 degrees, then 180 minus something bigger than 180 degrees, of course you expect that it's going to be negative. And when something is bigger than 180 degrees, if theta is bigger than 180 degrees, let me just do a little demonstration of what will be happening. So assuming my theta was bigger than 180 degrees, then this line is going to shift like this. So it will now be, let me say, somewhere here, something bigger than 180 degrees. And since it is bigger, so as you can see now, this point A has actually crossed this point -1 point, okay, and it has gone up ahead of it. So this is what we want to avoid. We will always want to make sure that the point A is always below this -1 point, or we can say the point A is actually shy of the -180 degree line. So for our system to be stable, the point A must be shy of this line always. It must not be above it. It must always be beneath this particular line. So anytime that the theta is bigger, it will now drive A above. So when you calculate 180 minus something bigger than 180, it's going to give you a negative value, and that means the system is unstable. So the summary of what I'm just trying to say is that for our system to be stable, this value, the magnitude of theta, irrespective of the fact that it's negative, it must be less than 180, or the phase margin must be positive. So when you do 180 plus this angle, it must be positive. In other words, it must be greater than 0. Okay, so we have seen how to determine stability from phase margin and gain margin. For stability, the phase margin must be what? Positive, and the gain margin must also be positive. Is that okay? So to summarize what we've learned, we learned about phase margin, gain margin, phase crossover frequency, and gain crossover frequency. Phase margin is the reciprocal of this guy. You take 20 log the reciprocal of this guy, 1 over alpha, where alpha is the distance from here to here. Now, the phase crossover frequency is the frequency that causes the magnitude, that's the magnitude alpha, to lie on this line. So you can say the phase crossover frequency is the frequency where our phase, the phase of this particular system, is -180 degrees. So it is on this line. Then gain crossover frequency is the frequency that makes the magnitude to be 1. As you can see, this is the magnitude. Okay, the magnitude at this point is unity because this is a unit circle. Okay, that's the phase, that's the gain crossover frequency. Gain crossover frequency, the frequency where the magnitude of this function is unity. Then you can call the gain, the phase margin, that's the angular sweep or the required angular lag that will drive the system into stability. Okay, the additional angular lag required for the system to be driven into stability, that's this phi of m. And you can calculate this phi of m by first of all determining this angle theta. Theta must be determined first. Theta is the phase of the system, and this phase of the system is calculated at this frequency. You calculate the phase of the system when the frequency is the gain crossover frequency, or when the amplitude of g of s is 1. That's how we'll calculate this phase. After calculating this phase, we'll subtract it from 180 to get the phase margin. So these are the steps involved. And in the next video, we are going to start solving exam questions in application of what we've learned so far in the Nyquist theory and in phase and gain margin. So thank you for watching this video. You don't have to panic, just go straight to the next video to see how we are going to solve all of that, what we've learned so far. So like and subscribe and stay tuned for more. Bye.